Okay, welcome back. We'll pick up where we left off at number 7. We'll try to get through number 10 on this video. Um, Number 7 shows a picture of a graph. Actually, it's the graph of the derivative, so you got to make sure you pick up on that little clue. And looks like a piecewise derivative function, so we're going to just go through statement by statement, starting with A and putting a true or a false. Um, we haven't really reviewed this much, so I'll kind of step to this one a little bit more in detail. Our question answer choice A rather says that the function is decreasing on -1 to 1, so all the way here. Now this is the derivative. The derivative is decreasing, but you notice that from -1 to 0 right here, the derivative is greater than 0. It's up here, it's positive 1 or 2 or whatever it is. It is decreasing, but anytime the derivative is greater than 0, then the function is increasing. So this part A is false, so we're not going to choose that one. Alright, looking at B, it's saying the function is increasing between -2 and 0. So at -2, it's positive here, and it stays positive until it gets to 0. So looks like B might be a potential answer, so we're going to put a true there. Let's go ahead and go through the other ones just to make sure. Is the function increasing from 1 to 2? From 1 to 2, remember the derivative is increasing, but the derivative itself is negative right here. It's negative all the way until it gets back to the axis, so the function itself is decreasing, so that's false. And the function has a local minimum at x equals 0. A local minimum on a graph, of course, looks like something like this, where the function is decreasing, then it has a horizontal tangent at this vertex, if you will, and then the function starts increasing. So when the function is decreasing, the derivative is negative, the derivative is 0 here, the derivative is positive over here, and that's just the opposite of what the graph shows us. To the left of the 0 point, it's positive right here. Then it hits 0, then the derivative would become, then the function would become decreasing here. So this is opposite of what they're giving us. That's false. This is actually a local max. And part E says the function is not differentiable at 1 and -1. Although the derivative is not differentiable there, we can't say anything about the function itself, so this one's false. So I'll go ahead and give you this one. The answer choice is B. Okay. Hope you followed that explanation. Let's move on to number 8. This should be one that's fairly simple for you. You notice here that we're taking the integral of x squared cosine x cubed. So right away you start looking at this and you're thinking you have to do some sort of u substitution. So the natural choice might be to make u equal this x cubed, and then the derivative of that would be 3x squared dx, and then solving for dx we get du over a 3x squared. So you can see that we have an x squared term right here, and now we have a 3x squared in our du term, so those x squares are going to cancel out for us, which is kind of nice. So rewriting it, we're going to have x squared cosine of u and du over 3x squared. So right away you can go ahead and make that simplification there. X squared cancels out, and we're simply going to have the integral of, pull out the constant 1/3, cosine of u du. So now just take the integral of this and substitute back in what u is equal to, and you should have no troubles with that one. Okay. Number 9, they're asking us to take I didn't finish writing this problem out. They're asking us to take the derivative and evaluate it when x is 0. So you just have to remember your derivative rules. Just a simple little reminder here. The derivative of ln of u is equal to what? 1 over u times the derivative of the u portion. So keeping that in mind, we just simply rewrite the function, make it a reciprocal, x plus 4 plus e to the negative 3x times the derivative of this. We'll place it right here. So that would be 1 plus 0, derivative of 4 is 0, constant, and this would be what? A chain rule for e to the negative 3x. So we have plus e to the negative 3x, and erase that real quick, negative 3x times, that would be negative 3, right? So if you clean this up, get it in terms of x, and then don't forget to go back in and substitute when x equals 0, and you should have a fairly straightforward problem. Okay? Let's move on to number 10. And number 10 is another one of those concept problems that seem to scare us sometimes. They give us a statement. They tell us that the function, its derivative, and the double derivative, or the second derivative, are all negative. So, and they've given us the graphs of the function, so make sure you pay attention to what they give you in your graphs. So let's take a look at the functions. A, B, C, and D, the functions are all negative, but the function in graph E is positive, so we're going to eliminate E right away and not have to mess with that anymore. So we'll just put a big X through that. Okay, let's take a look at the first derivative. So looking at A, let's see what this derivative looks like. The derivative is positive right here and negative right here. So if any part of the derivative is positive, then we can eliminate that answer. So we're going to get rid of this one. And it looks like C, if I drew it correctly, has a positive derivative, looks like everywhere. So we're going to eliminate C as well. And let's take a look at B. The derivative is negative all the way here. It's decreasing and it becomes decreasing more, right? For D, the derivative is also negative. I believe I drew that correctly. So we can't use that test. Okay, so here we're getting into a little bit of a section that we haven't gone over as much as we need to. We will after spring break. So the second derivative tells us one important thing, or several important things, but the first thing it tells us is the concavity, or whether it's concave up or concave down. Alright, so the simple test says that if the function is concave up, its second derivative is going to be positive, or in other words, greater than 0. And if it's concave down, the second derivative is less than 0. And when it's equal to 0, it's a potential inflection point. So let's take a look at the functions itself. It looks like B is concave down the whole time. See how this concavity is down? And in D, it looks like the function is concave down right here. That's a D, sorry about that. Concave down all the way here and here. But right here, it looks like somewhere in here the concavity switches and becomes concave up. So if it's ever concave up, the second derivative then turns positive. And since our statement told us that the second derivative is also negative, we are going to eliminate D, and that leaves us with only one choice. Answer choice B. Alright. Well, let me regroup myself here, and I'll take a look at a few more questions and get back to you in a little bit.